if and only if x1 equals x2. So another way of saying this is the outputs are equal if and only if the inputs are equal. Of course, if it's a function, then if the inputs are equal, the outputs are equal, right? So the stronger statement is that the outputs are only equal if the inputs are equal. So for instance, f of x equals x squared is not 1-to-1, since what? F of 1 is equal to f of -1. The square of 1 is equal to the square of -1. So the inputs are not equal, but the outputs are equal, right? And so when you look at the function, it satisfies a vertical line test, right? Because it's a function. But it does not satisfy a horizontal line test, right? So there's some horizontal line, say y equals 1, which intersects the function more than once. So two different inputs lead to the same output. That's not 1-to-1. So if it is 1-to-1, then if we know the outputs, we can figure out what the input is, right? The input is uniquely determined by the output, which is the opposite of the way it usually is. The output is uniquely determined by the input if it's a function. If it's a 1-to-1 function, we can also say that if we know the output, we can recover the input from the output without wondering. Like here, if we say, x squared equals 1, well, what squared equals 1? It could have been -1, it could have been 1, right? So if x is plus or minus 1, well, that's two different, so we don't know which input produced that output. If all we know is the output, then the input is ambiguous.
So if that's the case, does that mean it has to be linear?
Linear functions are 1-to-1.
Well, is that like a requirement? Because
No.
as soon as you go to
What
other...
other kind of functions are 1-to-1? Yeah, 1-to-1 functions include, as you say, f of x equals mx plus b. As long as m is not 0, that's going to be, should we say n is not 0? Then that's going to be 1-to-1, right? So in fact, you can say y equals mx plus b only if mx equals y minus b, which says that x is y minus b over m. And so we got a formula that gives the input in terms of the output. So we say that y equals f of x is equivalent to saying x equals f inverse of y, and this is the formula for the inverse function. So there is an inverse function. Here there is no unique inverse function, right? So we say the inverse function does not exist. Here there is an inverse function. Subtract b from the output and divide by m, and you recovered the input. So, which is a little, what makes this confusing is y was the output, and now y is the input. So you're reversing input and output, right? You're turning the machine around. It's like, is a soda machine a 1-to-1 function? What's the input? Well, you put money in, and you push a button, right? And then you get Dr. Pepper, or whatever. Can you put a Dr. Pepper in, get your money back, and unpress the button somehow? I'm not sure how you would unpress the button. But it would have to, reverse that process. And so a lot of functions in the real world don't work in reverse, right? But in math, there are some that do, and this is a good example. Linear function. How about a reciprocal function? So if this is y, let's use another example. Example 2. So can we solve for the input in terms of the output? Sure, 1 over y is going to be x minus 2, so x is going to be 2 plus 1 over y. So there's your formula, right? F inverse of y is equal to 2 plus 1 over y. Now, what makes it worse, as if this weren't already confusing enough, is that oftentimes, but then we swap the variables, because we like the independent variable to be named x. Right, so if you were to plot the inverse function and the function together, with each one having the same name for the input variable, then you would see symmetry across the line y equals x, because you're swapping x and y. So if we plot f of x equals, let's say, 2x plus 3, and then f inverse of x is going to be x minus 3 over 2. Is that true? I'm just following that formula there. So this is f inverse of y, right? So f inverse of x is the same thing, except instead of y, you got x, right? So, and b, I guess here is 3, so y minus 3, m is 2 over 2, right? So that works out. So what if you were to plot these two things in the same coordinate plane? Well, let's make a table of values for this one. All right, so -2, -1, 0, 1, 2. Okay, so this is -1, this is 1. Just keep adding 2, right? 3, 5, 7. It's a linear function, so you can follow that pattern, right? If you plot the inverse function, here's one way to do it. Just take these x input-output pairs and reverse them. So I'm going to write the what was the output of the function as the input to the inverse function. So if I plug in -1, what do I get? Well, -4 over 2 is -2, right? So that's just the reverse of this. -2 over 2 is -1. That's the reverse of this. 0 over 2 is 0. Again, reversed. 2 over 2 is 1. Reverse of this. 4 over 2 is 2. So let's plot those and see what's going on. So here's the y-axis and the x-axis. And I want to guess accommodate 7. Do I want to accommodate 7? How about just 5? We'll just go to 5. So y equals 5. 1, 2, 3, 4, 5. And x equals 5. 1, 2, 3, 4, 5. Here I'm trying to scale both axes with the same measure, which I don't know how well I did with that. Perfectly evenly spaced hash marks, right?